Title of the next section is Solving Rational Inequalities. In this section, we'll solve rational inequalities and check for possible solutions. First question, and only question for the section. 1 over 4a plus 5 over 8a is greater than 1/2. Solving the inequality, or rational inequality which has fractions, we first want to get common denominators. Looking at the numbers or coefficients 4, 8, and 2. The common coefficient or common number would be 8. So the first fraction we can multiply by 2 in the numerator and denominator. And the last fraction we can multiply by 4 in the denominator and numerator. The first two fractions also have the variable a in the denominator. So the last fraction will multiply by a also. So our common denominator would be 8a. Multiplying, the first fraction would be 2 over 8a plus the second fraction would stay the same. 5 over 8a is greater than 4a over 8a. Again, when we have fractions in an inequality, similar to an equation, once the denominators are all the same, we can cross those off or ignore those for now, and then solve the numerator part of the inequality. We'll have 2 plus 5 is greater than 4a. Combining like terms, we'll have 7 is greater than 4a, and solving for a, we can divide by 4. So we'll have 7/4 is greater than a, or if you rewrite the inequality, a will be less than 7/4. Similar to equations, we want to check for possible solutions. When we have an inequality, we'll look back at the numerator, or the denominator we crossed off, which was 8a. 8a again cannot be equal to 0. If it's equal to 0, then the entire equation or inequality would be undefined. So if we divide both sides by 8, we'll have a equals 0, which is not a possible solution for this inequality. Once you have the possible answer to the inequality, as well as answers that can be eliminated, what we want to do is look at a number line to eliminate any other possible solutions. For example, the 0 we put on a number line, and 7/4 we put on a number line. Separating the number line from 0 and 7/4, we'll have 3 sections. The first section is all the numbers less than 0. The middle section is the numbers between 0 and 7/4, and the last section is all the numbers on the right. What we want to do is pick a number from each section, plug it into the original inequality, and see which of these sections will work. For example, looking at the number 0, we can take a number to the left of 0, which would be -1. We'll plug a -1 into the original inequality. If -1 works, that means all the numbers less than 0 will be a solution. If -1 does not work, that means none of the numbers less than 0 will be a solution. The original inequality was 1 over 4a, or if we multiply by -1, that would be -1/4, plus 5a, but if we multiply by -1, that would be -5 over 8 is greater than 1/2. Simplifying this, or getting common denominators, we can change the first fraction into -2/8 minus 5/8 is greater than 1/2 is the same as 4/8. -2 minus 5 would be -7 over 8 is greater than 4 over 8. This inequality is false, since a negative number, or -7/8, is not greater than 4/8. So looking back at our number line, the left-hand side we can cross off, which means none of the numbers less than 0 will work for this solution. Our middle section, numbers between 0 and 7/4. And again, we can pick any number. Nice number to pick would be the number 1. Our original equation again, 1 over 4a, or if plugging in a 1 would be 1/4, plus 5 over 8a, 5 over 8 would stay the same, is greater than 1/2. And again, if this is a solution, then all the numbers between 0 and 7/4 work. If it's not, then none of the numbers between 0 and 7/4 will work. Getting common denominators again. 1/4 is the same as 2 over 8, plus 5 over 8, and 1/2 would be 4 over 8. Adding the fractions, we'll have 7 over 8 is greater than 4 over 8. 7/8 is greater than 4/8, which means in our solution we can circle the numbers between 0 and 7/4, which will work as solutions. And the last section, numbers bigger than 7/4. We can pick any number that is greater than 7/4. The next whole number that we could use would be 2. Plugging a 2 into the original equation, we'll have 1 over 4a, or 4 times 2, which would be 1/8, plus 5 over 8 times 2, which would be 16, is greater than 1/2. Getting common denominators again, the first fraction would be 2 over 16, plus 5 over 16, is greater than, changing 1/2 into 8 over 16. Adding the fractions, we'll have 7 over 16 is greater than 8 over 16. 7/16 is not greater than 8/16, which again means the section with 2, or the right-hand section, does not work for the inequality. The only section that works is the number between 0 and 7/4. So writing our answer as an inequality, we'll have 0 is less than, our variable a is less than 7/4. So any number between 0 and 7/4 is a solution. All the other numbers are not a solution. The title of the first section is Graphing, Exponential, Functions, and Domain/range. Exponential means the variable will be the exponent, and we'll find the domain and range, which, if you remember, is the same thing as the x values and y values. The first function that we'll graph is y equals 2 to the power of x. As with any new function we'll graph, first we will draw a t-table. You can use any numbers you want on t-tables, but with new graphs, the best numbers to use are -2, -1, 0, 1, and 2. This will give us some negative numbers, some positive numbers, and also the 0 value for x. The first number we'll plug in is -2 for the x value. That would be 2 to the -2nd. If you remember, with negative exponents, that means you put them on the bottom of the fraction and they become positive exponents. 2 squared would be 4. So our first answer, -2, would be 1/4. If you do the same thing for -1, 2 to the -1 power. would be 1 over 2 to the first, or 1/2. You plug a 0 in, 2 to the 0 power. By definition, any number to the 0 power would just be 1. So we'd have 0, 1 as our point. 2 to the first power would just be 2, and 2 squared would be 4. Once you have your table of values, you can draw your xy axis. The first point, -2, 1/4. -1, 1/2. 0, 1, 1, 2, and 2, 4 would be up higher. If you connect the points, they'll kind of curve up, and the left side will go parallel to the x-axis. The next question we'll graph is y equals 2 parentheses 1/3 to the x power. Same steps as before. We'll do a t-table. Again, the best numbers to use will be -2, -1, 0, 1, and 2. Plugging the first number in, -2 for the x. We have 2, 1/3 to the -2 power. Again, negative exponents mean the fraction flips upside down. So instead of 1/3, this will be 3 over 1, or just 3. And the 2 will be a +2. 3 squared would be 9. And 2 times 9 would be 18 for our first y value. Next x is -1. So 2 times 1/3 to the -1 power. 1/3 again flips over with the negative exponent. 3 to the first power would be 3, and we're left with 2 times 3, which would be 6. Plugging a 0 in gives us 2 times. 1/3 to the 0 power would just be 1, and 2 times 1 would be 2. Plugging a 1 in, 1/3 to the first power would just be 1/3. 2 times 1/3 would be 2/3. And the last point, x equals 2. 1/3 squared, square each of the numbers and you get 1/9. 2 times 1/9 would be 2/9. Graphing this function, again you can draw the xy axis. On the y value we'll go up to 18. And we'll have a couple points in the x and y direction. First point, -2, 18. And -1, 6. 0, 2. 1, 2/3 will be close to the x-axis, and 2 and 2/9 will be close also. Connecting them again, we'll have a curve going through the 5 points. Again, it will go parallel to the x-axis, and off to the left it keeps rising up. The difference on this graph is if you have a fraction as the base being raised to the exponent, it curves down to the right. If we had a whole number like we had 2 before, then it curves up to the right. The next section of notes is titled Right, an exponential function. In this section, we'll take 2 points and find the equation for the exponential function. The definition or equation we'll use for this section is y equals a parentheses b to the x power. All exponential functions are in this form where a and b can be any coefficients. The first problem will have 2 points, 0, 7 and 2, 63. Again, using these 2 points, we want to find an equation, an exponential function that passes through both of these points. What we'll do first is take our equation, and the first point, 0, 7, we'll plug those in for x and y. Y is equal to 7. A and b will leave as variables, and x is equal to 0. When you plug a 0 in for x, b to the 0 power is equal to 1, or it cancels out, and we have a is equal to 7. Once you know the value of a, then you can go back and take that same equation, and now we'll plug in the second points for x and y, and we'll also plug in a value for a. So using the second point, y is equal to 63, a we found was 7, b we'll solve for right now, and x is equal to 2. First step to solve for b is we can divide by 7. 63 divided by 7 would be 9. So b squared is equal to 9, or b is equal to 3. We'll take the positive square root. For exponential functions, b always has to be a positive number. If it's negative, then it's no longer exponential. But our final answer, y equals a, which is 7, b, which is 3, to the x power. So using 2 points, 0, 7, and 263, we can find the exponential function. Last section of notes today is titled Solving Exponential Equations. First equation we'll solve is 3 to the exponent of 2n plus 1 equals 27. Exponential equations will have variables in the exponents. To solve these, we want the bases, right now they're 3 and 27, to be the same on each side. What we can do for this problem is 3 to the 2n plus 1 stays the same, but 27 we can change so it has a base at 3. And that would change to 3 to the third power. Once the bases are equal, you can cross those off or ignore those, and then we'll set the exponents equal to each other. 2n plus 1 equals 3. Solving this, you can subtract 1 from both sides, divide, and you have your answer n equals 1. The next problem we'll solve is 16 to the exponent of n is less than 8 to the exponent of n plus 1. This time we have variables on both sides, and we also have an inequality rather than an equal sign. Same steps, we want to change these bases on both sides to be the same number. In order to do that, we'll have to change each base to a different number. For example, the 16 you can rewrite as 2 to the 4th power, and the n would come down. 8 you can rewrite as 2 to the 3rd power. Since we have a binomial exponent n plus 1, we'll put that in parentheses, so the 3 will be distributed to each of those. And again, once your bases are the same, both are 2's, you can cross those off and ignore those, and we'll set the exponents, in this case, less than each other. 4n is less than. The 3 we can distribute out, which would be 3n plus 3. And solving gets us the answer of n is less than 3. Last question we'll do for this section is 1 over 9 to the exponent of m equals 81 to the exponent of m plus 4. And again, we want to match up the bases on each side to have them be the same base. In this case, when we have a fraction 1 over 9, we can rewrite that as 9 to the negative 1 power. The m would come down, so it would be negative 1m. 81 we can rewrite as 9 squared. And again, when you have a binomial exponent, we can put that in parentheses, so when we solve it, it'll get distributed out. The 9's again are equal, and we have negative 1m equals 2m plus 8. We can subtract 2m from both sides and divide to get our answer. M is equal to negative 8/3. The first section of notes today is titled Changing, Logarithms, and Exponential form. Logarithms will be a brand new topic for this chapter, and exponential form will be similar to the graphs that we did earlier. The one definition for this section is log, which stands for logarithm. We'll have a small a, kind of like a subscript after log. We'll have a big B, which would be the base, and equals c. If you read this out loud, this would be log b base a equals c. And we're going to change that to exponential form. A is going to be the base, c will be the exponent, and it'll be equal to b. If you have three numbers in log form, you can match up the letters and switch it to exponential form, and vice versa, you can go from exponential form into log form. The only thing that changes is the log is not represented in the exponential form, and also b and c switch sides of the equations. The first problem we'll do is log base 5, 125 equals 3. Again, log 125 base 5 equals 3. If we want to change that into exponential form, a is equal to 5, b is equal to 125, and c is equal to 3, you can just rewrite it in exponential form. A would be 5, c would be 3, and b would be 125. So exponential form would be 5 to the third power equals 125. Also, you can take an exponential form, such as 8 to the third power equals 512, and we can change that into log form. Log form will start with log. Again, going back to the exponential equation, a is equal to 8, c is equal to 3, and b is equal to 512. We can match up the letters and rewrite it. So a would be 8, b would be 512, and c would be 3. So 8 to the third power equals 512. In log form would be log 512 base 8 equals 3. The next section of notes is titled Evaluate. Logarithms. First problem is log base 2, 16. For this problem, we can use what we just did with log equations to make this an equation. We can put an equal sign, and we don't know what it's equal to, but we can use a letter x to represent what the answer would be. Once you have a log equation, you can switch that around to exponents. Again, using a, b, and c. And that problem would be 2 to the x power equals 16. To solve this, we need to figure out 2 to what power would be 16. And that would be 4. So our answer, log 16 base 2, is equal to 4. Last question for this section will be log base 9, 243. Again, just like before, if it's not an equation, we can add an equal sign. We're solving for this expression, which we can set equal to x, and we'll find out what x equals. Switching this again to exponential form, the 9 will become the base, the 243 and x will switch sides, so it'll be 9 to the x power equals 243. For this question, we can try and figure out what x is equal to. 9 squared would be 81. 9 to the third power would be 729. So there is no integer or whole number that solves this one. What we can do instead, though, is change this 9 to a different base, such as 3. 3 to the second power would be 9. Bring the x down, and then we can figure out 243 would be 3 to what power? Multiplying out, it'll be 3 to the fifth power. And like the previous sections, when the bases are equal, we can cross those off and ignore those and set the exponents equal to each other. Solving, you get a fraction x equals 5 over 2. And again, there was no whole number integer. 9 to some power, that's 243.